The expedition went to the South Pacific Gyre, which is the lowest productivity part of the entire ocean, clearest natural water in the world. And we wanted to understand what life is like in the ancient sediment, in very old, very food-poor environments beneath that clearest water in the world. When we went out on this expedition, we set out to test that idea, core after core after core for the entire expedition. And we found that oxygen is present in all of the sediment. That suggests that in the abyssal clay of the world ocean, as long as it accumulates more slowly than a meter or two per million years, oxygen will penetrate all the way from the ocean to the basement. People knew that there was life in deep sediment near the continents, where there's lots of organic matter buried. In what's called the abyssal clay in the deep ocean, it was previously claimed that there was no life deeper than a few meters, and that was the ruling paradigm until we went. What we found was that life extends all the way from the seafloor to the underlying rocky basement. And what Yuki's paper now shows is that those organisms are not only alive in the deepest, oldest sediment, but they're capable of growing and dividing.
That expedition was the first time for me to join the IODT drilling expedition. So that was kind of the memorial cruise for me. And after that, I joined 6 different cruises, but the first one is always a first. So that is a memorable one. Our main question was whether the life can exist at such a very nutrient-limited environment. We were tackling how low the microbes can sustain their life in almost absence of their food. What I specifically tested feeding the microbes with their food or substrate and looking at their availability to incorporate added substrate or food into their cell body. Yeah, one of the surprising stuff is that up to 99.1% of the microbes could retain their activity to incorporate added substrate, meaning that they were alive and they kept their life for as long as 100 million years.
The most exciting part of this study is that it basically shows that there's no limit to life in the old sediment of Earth's ocean. That in the oldest sediment we've drilled, with the least amount of food, there's still living organisms. And they can come back to the world and grow and multiply.
The overall research took 10 years to complete. At the time, the technology is not good enough. It took me for, let's say, 3 to 4 years to confidently develop such kind of technologies to investigate the life in such a low abundance or very low in metabolic activity. Selectively separate microbes from the sediment inorganic particles. And the other is the nanoscale secondary ion mass spectrometry, in short, nanosyncs. Very much critical for this research since that instrument can look at the microbes in terms of incorporation of the added nutrient. The stable isotope is a little bit slightly heavier. Those isotopes are sharing almost same chemical property. Also, it is incorporated or metabolized by the microbes or even us in the same manner. The ultimate thing occurred is that their cell body or microbes weight get a little bit heavier than the one which did not incorporate the added stable isotope. So it is like a weight scale for the microbes. The subseafloor biosphere is a very good target to probing the existence of the life or extinction of the life in that environment. The subseafloor biosphere is a very good target to investigate or explore for the limits of the life. Lifestyle of the subseafloor microbes, they are living in a very scarce nutrient environment, so their life should be very slow. Also, the evolutionary speed will be slower in a subseafloor. So that is why I want to look at the life in a subseafloor in terms of the evolutionary concept. Last year, I joined the other expedition on same vessel, Joyous Revolution, looking at the life or limit of the life at the very hot subseafloor environment. So I'm looking forward to having the life at the another extreme condition.